Good afternoon and welcome to today's midas FEA webinar. My name is Robert Salka and I work as a structural engineer for the technical department of midas UK. Today's session will cover a detailed design of an Anchorage block, and we will see how midas FEA was used for this. Firstly, let's look into the contents of today's session. We will start with the purpose of this webinar, followed by an introduction to midas FEA. Then we will see what reference materials were used for this, then the details of the analysis, followed by a check of the results, and we'll see also what conclusion has been drawn after this, and what future research possibilities there are. So firstly, the purpose of today's webinar is to analyze different solutions for the anchorages of post-tension structures using advanced nonlinear models. We also want to compare theoretical models to what we have found from the analysis, and also, very importantly, to check the crack distribution. And also, using different solutions, we would like to compare how high-strength concrete behaves and how ultra-high-performance fibre-reinforced concrete behaves. We would like to see a comparison between these two materials, and also we would like to see how the reinforcement affects the stress distribution and the crack distribution in the concrete. So firstly, let's see what is midas FEA. So midas FEA is a finite element analysis software capable of dealing with advanced nonlinear analysis. It can be used for both global and local analysis. It is capable of dealing with very complex geometries, which makes it perfect for local analysis, and its analysis features allow it to carry very refined and highly accurate analysis. So first, let's see what application areas are for midas FEA. Obviously, it can carry linear static analysis with both including different load cases, load combinations, and different solvers, and it can also carry construction stage analysis, both linear and nonlinear analysis. In addition, nonlinear static analysis can be carried, including both material and geometric nonlinear analysis. It has in its database different nonlinear models, such as von Mises, Ductal, and also different iteration methods. Also, very important for today's session, we can consider reinforcement as reinforcement elements in midas FEA. Sorry, this can be embedded in plate elements or in solids, and we can consider normal reinforcement and also pre-stressed reinforcement. Also, we can carry a crack analysis with midas FEA, so we can check the crack status, the crack development, and the stress levels, considering the cracking of the material, concrete in this case. Also, eigenvalue analysis can be carried, so we can do model analysis, check eigenmodes, vibration modes for it, and also carry linear buckling analysis. In addition, dynamic analysis, both as time history analysis or including spectrum functions, can be used. So different types of dynamic loads can be considered in the models, and also for seismic stones, we have a spectrum of, we have database of spectrums or a seismic data generator that can be used for something like this. Other analysis types include considering nonlinearity of interface, contact analysis, again including material and geometry nonlinearity. Also fatigue analysis with different methods including rainfall counting and SM curves. Also heat of hydration and heat transfer analysis can be carried, and also for 2D, in 2D we can carry a CFD analysis. So now let's see a bit how the software looks like. So I have here a new file in midas FEA. For those of you that haven't used the software yet, you can see here that we have the main menu. We can find all the commands from the software here, and we also have these as shortcuts for each menu, so we can access every function directly from the shortcuts, and also we have shortcuts on the side for viewing and rotating options. Also very useful, the workstream menu. First we have a pre-work and post-work stream menu. For the pre-work we can see everything that can be found in the model. Here we can edit from here, isolate, make changes to the model, and it's very easy to check what is in the model. And for the post-work we can see all the results for different analysis, for different stages, and we can check each type of result separately. As I said, midas FEA is very versatile. We can model very complex geometries. We can start by modeling, by creating points, curves, surfaces, solids. We can start from scratch. We have generators of different what we call primitive features, or we can even import very complex geometries from CAD. So for example, we can import, let's say, a STP file. I have a model here. We can change how the software imports the geometry and how it treats it. But just for this example, I will import it as it is. You can see now that the software is reading the STP file. Once the geometry is imported, we can modify it. For example, for this analysis, we wouldn't need all of these details. So what we can do is modify it. We have Boolean operations. We can fuse it. We can delete. We can cut. Also, having surfaces or lines, we can also generate directly some sections. And for example, parts that will be connected to this, we can generate it directly. We can remove faces, edges of these sections, so we can edit this and simplify it to wherever is needed in our model. Now I will switch to a model that has the geometry of what we will use today, just so that you can see what we will use today. So I will switch to our model. As you can see, this is the Anchorage block that will be used. We have, as I mentioned, points, curves, surfaces, and solids. Let me show you firstly the different parts. So we have the trumpet, or the Anchorage system. We can either import this just as shown before, or we can even import a 2D CAD and revolve this to create a solid. We also have the Anchorage block. You can see that the Anchorage block is empty on the inside to accommodate the cone, and also we can see the hole where the tendons will go through. To create this, we have used simply a cut option. So we have the part that will be extracted from the main block, and then using the Boolean operation of cut, we have simply created this function. As I said, midas FEA is very has very complex possibilities when it comes to meshing. So from here we can use auto mesh or map meshing functions. These differ from the type of elements that can be used. So for example, map mesh will generate quadrilateral, pentahedron or hexahedron elements, while auto mesh will generate triangular, quadrilateral or tetrahedron tetrahedron meshing. Here we have different options. So for example, if we want to mesh a solid, we can select it, choose the meshing size of it, choose a property for it, and then give it a name to the mesh set, and also choose how advanced options can be, what advanced options will be used. So for example, if we have an edge and we want to mesh to that edge, or we have inner points or edges within the solid, we can select them and choose the meshing for them and what properties will be used. Also, we can choose the refinement of the mesh, and if we want, we can have a manual seeding, what mesh sets to the new mesh should be placed under, and very important, when we have different elements that need to be connected, as in this case we have the trumpet and the concrete block, we can choose to merge nodes. So if we have the merge nodes options, then the nodes of the trumpet, the nodes that on the surfaces that are common between the trumpet and the concrete will be merged, so they will be the same. And in this way, if we have, for example, a slab and a concrete beam, we can generate the interface between them, and we can choose the roughness of the interface. Or in this case, we can assume that they will work perfectly together. So, for example, let me just select the element. We can see a preview of the seeding, and we can click OK, and we will generate the meshing. Also, to generate the meshing of the block, we can use the same auto mesh function. So let's say for this we don't need such a refined meshing. So we can choose the property being the material. We can give it a name, block, and as I mentioned, here is very important to have the merge nodes on. So now we can mesh. And as I mentioned, now we can see the two meshes generated. We can choose display options for them. We can display the IDs for both meshes and use the shrink function. Now if we zoom, we can see that the nodes here have the same IDs, so 874, meaning that now the meshing of these elements share the node, so they will be connected. Now I will go back to the presentation, and we'll continue with, and I will go through different details as different modeling options and details of the modeling as we go through the presentation. So The reference material for this webinar, so we use different reference materials for this webinar. We have used Bureau Code 2 and also Syria, and also a very good thesis by Anna Spasojevic, structural application of ultra high performance fiber-reinforced concrete in the design, and also a phase GC etc. And also a paper by Toulemont, Renault, and Levant, testing and analyzing innovative design of ultra high performance concrete anchor blocks for post-tension tenders. So now let's look into analysis details. What Anchorage system has been used. The geometry was provided by Freyssinet. You can see the general geometry here. This is similar to what was used for the Hammersmith Flyover in the phase 2 rehabilitation. The material used for the anchor system, so for the strumpet and the bearing plate is S355, and the nonlinear model, the plastic model for it was midas. We have used a curve C elastoplastic with linear strain hardening as per the Eurocode, and you can see how we have defined this in the software. And now I will go back to midas FEA and show you the properties of the trumpet. So here I have a model with that is already meshed and analyzed. I will isolate just the trumpet, so we can see the meshing that was used. And the material, as I mentioned, S355. We have the material properties here, and then the constitutive model, von Mises as I mentioned, and the function for straight hardening. We can define this directly from here, and we can see what has been used directly. So as I mentioned, we have used this. The meshing for this, the meshing used for this was of 20 millimeters. Now, the property was created using what we call 3D properties. So, let me show you. So when we create a property, we can choose what type it should be. So, going back 1D, 2D interface reinforcement. This is a 3D reinforced 3D property, and we just give it a name and assign a material for it. So to create the material, just as explained before, we create a material, assign a function, and then add it to the property. And then when we use the meshing function, we can choose what property to be used for the given solid. Now for the Anchorage block, the general dimensions are 0.6, 0.6 and 1 meter. We have used 2 different cases, in total 4 different cases. We have separated them into using high strength concrete and ultra high performance concrete, and also having one model without reinforcement, so plain concrete, and the other model with reinforcement, and only the bursting reinforcement was considered in this analysis. And now let's see the details of and for these, the total strain crack model was used to carry the crack analysis. And now for the first model, the one using high strength concrete, C90-105. You can see the mechanical properties defined here, and also the constitutive model used. So as I mentioned, we have used total strain crack model. And now the details for this model, I will discuss about each one of them separately. So midas FEA can, with the total strain crack model, can use both fixed and rotating models. These are under the so-called smear crack model. The fixed crack model assumes that once defined, the axis of the cracks will not change, so they will as we increase the load, they will carry in the same directions. Whereas the rotating crack model assumes that the crack axis will always change depending on the principal strength. In this analysis, we have used the rotating model. Then we can choose what type of how the stiffness matrix should be treated. We have a second or a tangent option. Both of these are suitable for cracked concrete, and you can see the details of them. One is very suitable for getting a good convergence for this type of analysis, and the other is very good for local cracking and crack propagation. Also, we can consider the effect of lateral crack. So what this does is, because of the tensile stresses perpendicular to the direction of the main compressive strength, the compressive strength of the concrete will be decreased, depending on the so-called lateral damage variables, and this can be considered in the model by considering Q and Collins. And also, if we have confined, we can also consider the confinement effect. So we can consider that the strength of the concrete is increased due to lateral confinement, and for this a linearized Torrenfeld curve can be used. As we apply the load in this model uniaxially, we apply it just as a straight load from the top, and we don't consider the reinforcement cage. We are not considering confinement in this analysis. And then for the nonlinear properties, we can define the tension, compression, and shear functions. The tension function suitable for checking cracking in reinforced concrete is the Horn-like model. This accounts for the tension softening behavior, and it can be defined by using three parameters. Obviously, tensile strength, the tensile fracture energy, and the crack bandwidth. The tensile fracture energy is dependent on the modulus of elasticity, the tensile strength, and the crack bandwidth. Now, the crack bandwidth is a variable on which there is little consensus on how it should be defined. This is very dependent on element type, material properties, mesh size, but as a general rule, it can be used as the square root of the size of the mesh elements. For the compression curve, a Torrenfeld model is used, and for this we just need to input the compressive strength. Obviously, all the details for these functions can be found in the analysis manual of midas FEA. And now let's see how the high strength concrete was defined in midas FEA. So I have here one of the models in which I used C90-105. I will isolate just the concrete block. So this is the concrete block, and we can see the reinforced concrete properties. So we have C90-105. We can see the mechanical properties, and then the crack model that was used, and the tension function assigned to them. I forgot to mention about the shear function. As for now, we can only consider a constant element in the shear function, and this is only applicable for the fixed crack model. So for the rotating crack model, the shear function will be ignored. And the functions that I have mentioned, the tension function, we can see the function type as Hordijk and the properties that were used. As I've mentioned, these were calculated depending on the mesh size and the tensile strength. We can see how the function looks here, and also the compression function using the Torenfeld curve, and the shear function. But as I said, this is ignored when we use the rotating crack model. Now, going back to the presentation, the ultra-high performance fiber-reinforced concrete properties are those for the Ductal G2TM. This was again provided by Freyssinet, and this is a concrete that was used in one of their projects. We have here the characteristics of the material. We can see FCK 150 megapascal, tension 8 megapascal, and a modulus of elasticity of 53 gigapascal. The curve, the stress strain curve used for the behavior of the material was the one used at SLS. So, considering the material properties, we have calculated the stress and the strains for defining the curve. We have here the details used for the compression curve and for the tension curve. And as this is a local analysis, a K factor of 1.8 is needed, but this is also to be checked with tests. But for the purpose of this webinar, we have used a K local of 1.8. So the tension and compression curves, as we have calculated the properties using the functions provided by Ductal, we have modeled them using multilinear functions. So going back in midas FEA, I have here a model that uses the dry performance fiber-reinforced concrete material. So I will isolate. You can see the Anchorage block and the material properties. So we have G2TM, the mechanical properties, and the constitutive model, and the functions. Looking over the functions, we can see the tension function and also the compression function. And these, as I mentioned, have been assigned to the main material. Now, as I mentioned, we have used 4 different models, 2 of them using high-strength concrete C90-105 and the other using ultra-high performance fiber-reinforced concrete. But also we have used 2 models with plain concrete and 2 models with reinforced concrete. So now let's see the details of the reinforcement. So the material for the reinforcement was B500C. We have used 2 spirals. So as I mentioned, we have only considered bursting reinforcement. So two spirals, one of a radius of 200 millimeters, and the other spiral radius of 250, with a bar diameter of 10 millimeters, and we have followed the guidance of Syria, so the spiral diameter is at least is at least 50 millimeters bigger in diameter compared to the trumpet, and also is distributed within a region of 2 times YP and smaller than 2 times YO. Going back to the model, we can see the reinforcement properties. So now I will isolate just the reinforcement. So we have here the spirals. As I've mentioned, we can mesh. We can firstly define properties for the reinforcement. So we can consider a reinforcement element, different types of reinforcements, a bar section, a grid or a grid section, and we can choose if it is a tendon or a reinforcement. We can assign a material and define a cross-section area. And then when we use the meshing function, we can choose an edge, and then assign it as reinforcement. And you can see we can add as a bar in plane stress, bar in plate, or bar in solid. And the properties can also be checked in the workstream menu, as I've mentioned, cross-sectional area and material used. Now for the analysis details, as I've mentioned, we've considered the concrete block and the Anchorage block and the barrier plate, so the trumpet. We have applied the pre-stress load as a pressure load on the top of the trumpet, just for simplicity, and a total load of an equivalent of 30 strands, tensed at 180 kilonewtons. We have also used a factor of 1.2 for favorable load as per Eurocode 2. Also, the self-rate was applied using a self-rate function, automatic self-rate function, and the supports are applied as restraints to the nodes at the base of the concrete block. Now again, going back to FEA, we can see how the loads have been applied. So in the analysis, we can assign, firstly the boundary conditions, we can assign different types of boundary conditions. We can assign them to nodes, to faces, to curves, or faces of nodes. And now they have been assigned to the node at the bottom of the section, the bottom of the concrete block. And the load as a pressure load, again we can apply it to faces of 2D or 3D elements or to surfaces. And in this case, it's been applied as a pressure load on the bearing plate. So let me highlight this. Now, before checking the results, let's see how different analysis can be defined. So if we have a model with the geometry, meshing, and loads added, we can easily define different load cases. The good thing in FEA is that we can analyze only specific cases at a time. So for example, in the analysis we can define different analysis cases. We can give it a name and choose what type of analysis it is, static analysis, history, and then we can choose what mesh elements and what boundary conditions to be used and what loads to be applied. And also we have an output control where we can choose to have results only for given meshes, and also we can choose what type of results to be stored. And also we have an analysis control. For the nonlinear analysis, we can also incorporate, we can also have crack analysis results calculated, and also analysis control is much more versatile. We can include material nonlinearity and geometrical linearity, and what type of iterations we want to use, so different iterations methods, and also how load steps and how many load steps to be considered in nonlinear analysis, and details about the convergence. Now we'll show how different how results can be read in midas FEA, and then we will. So I will show you how the results can be read, how different types of results can be read, and then we will go into the comparison between the two. In the presentation, I will show the results for different models, and we will analyze them. Now I have a model here that has ultra high performance fiber-reinforced concrete model with the reinforcement. So as I mentioned, we have the workstream menu with all the properties of the model, two analysis cases, a linear static and non-linear analysis. As I said, when we run the analysis, we can choose what type of analysis to be carried. Now in the post works, we can see the results for static analysis and for non-linear analysis. For each of the steps, we have used 5 analysis steps, 5 steps for adding for the load application and the non-linear analysis. So we have the results for each step. The results are separated in reactions, displacements, strains, stresses, results for the reinforcement and the crack status. And we can also, so as I mentioned, we have the results for different cases, and we can check results for each mesh set separately. So for example, if we want to check the results for the trumpet, so we can show like this, and we can check, for example, stresses in the legend. We can check midas stresses directly, and also very helpful different options as isosurfaces. We can check for different stress values, so we can set the stress value and check it for the given stress value. Also slice planes, so we can choose a slice over a direction, a position, and a direction to go from, and also clipping planes. Also for these results, we have many different options. We can extract results by selecting specific elements for different load analysis and for different components and load cases. We can also probe results, what we call probe, so we can choose different nodes. We can check the results for each node, or we can check for absolute maximum, and they will be highlighted here. If we change the result type, the values will be updated for each node. And also, going back to original, check results for the concrete separately as well. We can check both the contour and the vectors. So, for example, we can see the stress distribution for the sigma 1 stresses, or for the maximum tensile stresses and maximum compressive stresses. We can also check results directly for the reinforcement. So if I show the reinforcement, we can check stress values and strain values, and also for the concrete block. We can check the crack status. This is a very fine model. The machine is quite big, so it takes a bit of time to load. But normally for this type of analysis, it is ideal to carry a convergence analysis and see how many degrees of freedom are needed for the analysis to give correct results. And now we can see the status at each in the concrete block. So if the crack is open during loading, unloading it's fully open, or if it's closed. And also we can check the pattern. So we can check the stress in the concrete normal to the direction of the crack, normal to the crack, or also the shear stresses, the ones tangent or second to the crack, with each of them with the stress value. So this, we can check against the legend, and we can see the stress values we have. Maybe it's better if we see from the side. And now seeing how results can be read in the software very easily, I will go into the presentation and we will directly compare the results from the different solutions. So as for the stress distribution, as the serial guide suggests, for this type of Anchorage block, we would have the compressive stresses running parallel to the load, and the tensile stresses perpendicular to it. As you can see, the sigma 3, so the maximum compressive stresses, match perfectly the solution as per Syria, and the tensile stresses as well. You can see these are the vectors for the stresses. So maximum stress sigma 1 matches the tensile stress here and the compression stress as well. Now we will go directly into the comparison between the different solutions. So as I mentioned, we have 4 models, 4 cases: high-strength concrete C90 105 without reinforcement, with reinforcement, and ultra-high performance reinforced concrete G2TM with reinforcement, without reinforcement, and with reinforcement. These are the results at the last step of the nonlinear analysis. So now we have the entire load applied on the concrete block. So we have full PT. We can see that the stress, these are, so as I mentioned, these are sigma 1 stresses, so principal stress, tensile stresses. We can see that for the C90 105 without the reinforcement, I have mentioned here that we have 0.85 PT. This is because without having the reinforcement, the model fails before reaching the full load. We can see that the stress distribution, when we have only 85% of the load in the model without the reinforcement in the plain concrete, is very similar to the stress distribution in the model with reinforcement. We can see that we have peaks around the concrete, or around the trumpet, and in parts of the model. When we consider the ultra high performance fibre-reinforced concrete model, we can see that there is not much difference between the two solutions, having or not having reinforcement. The stress levels are fairly similar, and we can see the distribution is very similar as well. So the concrete works well even without the aid from the reinforcement. Now when we check sigma 3 stresses, so the principal stress sigma 3, we can see that for the high strength concrete, when we don't have reinforcement, the stress level is also it's even much higher when we have only 85% of the load compared to the full load in the model with the reinforcement. We can see that we reach a maximum compressive stress of about 66 megapascals, whereas in the model with the reinforcement, whereas in the model without the reinforcement, even at 85% of the load, we already have 82 megapascals. So as we increase it, we fail the model. For the ultra high performance fiber reinforced model, again we can see that the stress distribution is almost the same. The material works well even without the presence of the reinforcement. The distribution is almost the same. Now when we check the crack status, here I have a small explanation of what the software provides. We can see a stress strain curve and the different results that we provide. We have partially loaded, partially open when loading, so we can see that the strain keeps increasing in the range of plasticity. Before plasticity, we can start with the elastic domain, where we basically have no crack yet, and then partially open during loading, the strain in the element increases in the range of plasticity. Then we have partially open unloading, where the strain decreases in the range of plasticity. Then fully open, the strain in the element increases even though we have now zero stress in the element. And for the fully open unloading, the strain increases when we have zero stress. And when we have closed status, the strain increases in the range of plasticity, and it decreases until it reaches zero. And as I mentioned, the elastic state where we have no crack yet. Now going in the comparison between the four models, we can see that the stress distribution in, so we see that we have, as I mentioned, partially open, fully open loading, fully open status. So we have fully open even at 85% in the model in the high strength concrete without reinforcement, which is a fairly similar distribution to that of the reinforced concrete at the full load. We can see that if we go to 95% of the pre-stress load, basically the model fails. It is difficult to difficult to get convergence in the model, and as you can see, everything is basically cracked, fully open. Whereas in the ultra high performance fiber reinforced concrete models, both have just partially open cracks. We can see that the two solutions, with and without the reinforcement, behave fairly similarly. there is just a very small amount of difference, a very small contribution of the reinforcement to the crack distribution. If we look from the side, we can also see again how the stress distribution affects, how the reinforcement affects the crack distribution in the normal concrete, in the high strength concrete. We can see that if we go to 95% of the pre-stress load in the high strength concrete without reinforcement, the model is fully cracked. Whereas when we consider ultra high performance concrete at the full load, we can see that the two solutions behave fairly similarly. There is just a slight improvement in some areas when it comes to crack distribution, but again the model is still in, so all the cracks are still partially open. If we check a progression of the models without the reinforcement, we can check, I have compiled the behavior at being 20% increments. So we can see that we have a small progression of the cracks, and when we reach 80% for the high strength concrete without reinforcement, we already have fully open cracks, and at only 95% of the load, everything is basically cracked. Whereas we can see a gradual increase in crack distribution in the ultra high performance fibre-reinforced concrete model, but we don't have fully open cracks yet. Everything is partially open. In the model with the reinforcement, we can see that again the increase in cracks is open. There is an increase in crack pattern, but considering the two solutions, we have fully open cracks in the high strength concrete compared to no fully open cracks in the ultra high performance fibre-reinforced concrete. Now, to put into perspective the way the cracks develop in the ultra high performance fibre-reinforced concrete model, I have checked the stress and the strains against the stress strain curve. So we can see the principal stress distribution for the ultra high performance fibre-reinforced concrete without reinforcement here, and this principal strain distribution here. I have plotted the stress strain curve, and I have taken the most loaded element, in this case 102.925. This element has the maximum strain and the maximum stress. You can see that this is on the plateau of the tensile part of the high strength of the stress strain curve. So basically, the concrete deforms, it reaches cracking, and then the fibers kick in. So we can see that now, even at the full load, the fibers benefit. So the fibers take the stress, and we don't. So we're not relying on the concrete so much anymore, but on the fibers themselves. Now we can also check the stresses in the reinforcement, and we can see how the two different types of concrete work together with the reinforcement. If we check the stresses and the strains, we can see that the high strength concrete, the C90 105 reinforcement, has a very doesn't have a uniform distribution of the stresses in the reinforcement. We can see that we have a general stress distribution where we have these peaks where the concrete simply doesn't work at all, and now the reinforcement has to take the entire load. We can see that we reach very high stress values, 358 in this case, megapascals of stress at specific positions. When we look at the ultra high performance fibre-reinforced concrete, we can see that the stress distribution in the reinforcement is much more even. We can see that most of the reinforcement works at the same stress level, same stress level. So we can conclude from this that the fibers work much better in the model. In the concrete they take a lot of the load, and they help distribute the stresses more evenly within the mass of the concrete. And now the reinforcement also is loaded more evenly. They work together in a much better manner. Now, to conclude, we can from the test that we've carried, we can see that the bursting reinforcement has a very beneficial effect on high strength concrete. For the case that we've considered, without the reinforcement, the high strength concrete couldn't take the entire load. Whereas when we consider the ultra high performance concrete, the reinforcement had little to no effect in both the stress levels and the crack distribution. And ultra high performance concrete has a more even distribution of stresses, both in the concrete mass and in the reinforcement. And we have concluded that the fibers have a very beneficial effect on both the crack distribution and the stresses. And as you can see, as you have seen in the results, the dimensions of the cracks are limited very much by the fibers. If you remember, we were only in partially open cracks, not fully developed cracks. Now, obviously, this type of concrete is ultra high performance fiber reinforced concrete is, let's say, fairly new to this. There is not much work. There has been much work done for it, but not nearly enough. So in the future, it will be very interesting to be able to check the theoretical models adopted with tests on ultra high performance concrete samples, and it will be ideal to calibrate these models to the tests. Also, something that we are very open to is to implement ultra high performance fiber reinforced nonlinear models in the software, and also include databases of these types of materials. So we would like to have it in our finite software. And also, it will be very ideal. It will be ideal to have a better implementation of this type of concrete, of ultra high performance fiber reinforced concrete, into the design standards, because as you know, currently the standards are ultra conservative, and at the moment there is not much. They are not very covered. For example, in the Eurocodes. Now there is some work done in France for this, and it will be very interesting to see how they include fiber reinforced concrete in the Eurocode. Also, midas is very open to working with this type of concrete, so please feel free to contact us for future cooperations on improving the implementation of ultra high performance fiber reinforced concrete in our finite element software. And I would like to thank you for your attention. Please contact us. Feel free to contact us at uk@support@midas.com. If you have any questions about this webinar or about future presentations, or if you need support on one of our softwares, please feel free to contact us. And you also have a phone number from the management department in. And you can also find this webinar on our uk.midas.com website. There you will also find the video and the presentation, and many videos and presentations from webinars that we have done in the past, and also every news about future future webinars or events that we will have are posted there. And you can also see different software that we have also on our website, and you can also follow us on different social media platforms. Again, thank you for your attention, and looking forward to hearing from you for both queries or future cooperation. Thank you, and have a nice day.